Hello everyone, and welcome back to the Kohi Game Engine series. Today we are going to be tackling threads and mutexes on Windows. So before we jump into the video, I would like to take a quick minute and thank the partners of the channel. The partners are the highest tier support both on YouTube and Patreon, and they are Caden, Eearslya, Gerboles Inc., Super Awesome, and Wensheng. I'd also like to thank all the other fine folks that appear on the screen here. Your support is greatly appreciated. Thank you very much. If you'd like to support the channel and support my work, feel free to have a look at the YouTube membership, or if you prefer Patreon, you can check out patreon.com/TravisVroman. So as an extension of the last video, today we are going to be taking a look at the platform layer on Win32 and implementing our platform changes for threads and mutexes for Windows. While we're here on Windows, I do want to also fix a few just minor issues that have come up that you guys have mentioned. We're going to be doing a much larger sort of bug pass at some point, but for now I do want to go ahead and get this sorted as well. So the very first thing that I want to do is I actually want to go to the make file. So I'm going to say windows.make. And we actually want to add one more thing to our defines. We want to just turn off CRT security warnings because we don't actually we don't want those warnings to be taking place. So just to be consistent kind of with some of the other libraries that we have in place, I want to go ahead and turn that off there. So that's that. I do also want to go to application because there is something that currently is happening with the application where we are not quite starting off at the correct window size when we load up the application. And this is more than likely due to some of the back-end changes in terms of how the resizing logic actually works. But we're going to go ahead and just patch this for now, since we're likely going to be revisiting that code anyway in the near future. So what we're going to look at is within our application create, right here before we call the app state game instance on resize, we're also going to just call the renderer on resize. And this will make sure that the renderer is up to date with the most current window size and the correct window size. So that way when it goes ahead and sets up the frame buffers and whatnot, those things are all at the right size without us having to recreate the window, or resize the window rather. One other thing that's come up is in file system C. So there's a little bit of a bug in here with the file system exists function. So the Linux version of it actually had this implemented correctly, where the return stat equals 0 is whether or not the file exists, but in the Windows version, we are just returning the result of stat, which is not correct. We actually want to do the same check by double checking it against 0. So that's a simple fix, but it will get this up and running again. And we'll go ahead and when this gets merged in, we'll go ahead and close out the bug report for that as well. Okay, so all of the rest of our changes are going to be in our platform win32.c. So the first thing we need to do is go to the top, and we need to include right here after our other core files, we need kthread and kmutex. And then we're going to go through and basically implement the various platform and thread functions that we need in place. So we're going to go to sleep, platform sleep. And right after that is where we are actually going to put our first function, which is platform get processor count. So similar to what we did on the Linux side, this just makes the Win32 appropriate calls to get the number of processor cores that we have. So we just make a call here to get system info, passing the address of this structure here. It fills that out, and then we can say sysinfo.dw number of processors gives us the number of logical cores that we have. We go ahead and write that out as an info and then return that number as the processor count. So that is that. The next thing we're going to do is we're going to say note begin threads. And the first thing that we're going to do is our kthread create. So we're going to fill this out just like we did for the Linux version, only we are going to use the Win32 API calls instead. So we're still going to check for the existence of a function pointer, the start function pointer, and fail on that if we do not have it. The next thing that we're going to do is call a function called createThread, and this is provided to us by windows.h. And what we can actually do is, let me go ahead and open up a new browser here. So all of this documentation can be found in MSDN in terms of how these functions work. I've already gone ahead and read this documentation so that I'm fully aware of what we want to actually pass to all the arguments and so forth. So what we are doing here is in createThread, the thread attributes, we are passing nothing because we don't want any specific thread attributes. The stack size, we don't want to use a custom stack size for this thread. You can actually specify that. I'm not sure why you would ever really want to do that, but they do allow you to do that. They do allow you to have the ability to do that. Maybe if you were writing a debugger or something is the only thing I can kind of think of that you might want to do that, but I can't really understand why you would want to actually do that. But anyway, the next thing is the LP thread start routine, and that's this start function pointer here. So all that is a typedef, which is returning a D word, which is an unsigned long. And then it's a Win API, which is just a standard call, pthread start routine, and that takes a LP void or a long pointer to a void to some parameter. So ultimately, this is just a unsigned integer that it returns, and it takes a void pointer essentially. So we already have that. That basically matches up exactly with what we have for our function pointer definition here. We have a U32 return, and it takes type void pointer. Next, we go ahead and pass our parameters, which can be anything because it is also a long pointer to a void. So that is just a void pointer here. And the next property is creation flags. We're not using any of those. And then a long pointer to a D word, which is going to be the thread ID. So this is basically a D word pointer where it saves to the address of outthread thread ID, which is the U64 in this case. And we just send it the address of that and cast it to a D word pointer so it's happy. So this is a very similar API to the pthread library. A lot of these things will kind of line up with things that we've already seen. It's just a little bit different using Windows types and so forth. So the next thing we'll do is go ahead and spit out some debug saying we're starting a process on the thread ID using the same formatting as we did elsewhere. We will then go ahead and check to make sure that there is some sort of internal data that has been assigned. So the internal data should have been assigned by what is returned from createThread, which is just a handle. So that's a lot of things in the Windows API just returns to you a handle. And it's just a sort of an opaque handle that is used for various resources like Windows or threads, things of that nature. And so that is just saved off to the internal data here. And we just check to make sure that we actually obtain one of those. Next, if we want to go ahead and auto-detach, then we're going to call close handle, which just takes the thread internal data, which is a handle returned from createThread. And all this means is basically the same thing as before, is that we don't really want to manage this anymore. We don't really need to maintain the handle to it anymore. We don't have a need to track it anymore. And so we can get rid of the handle. It will not get rid of the thread, it will just close out or kill the internal data or the handle to this. So that essentially is the same as a pthread detach. And then finally, once we get past all that, we return true. And that is thread creation in the Windows API. So next is destroy. And obviously, the only thing we need to check here is, first off, do we have a thread? So we should probably check that. And if we have thread internal data, okay? And all we're going to do here is we are going to, first off, call something called getExitCodeThread. So if we go ahead and look this up, here we go. Retrieves the termination status of the specified thread. And this can return a whole bunch of things, but basically it says if the function succeeds, the function that the thread was started with, the return value is non-zero. If the function fails, the return value is 0. And then if we wanted to get extended error information, we could call getLastError. So in this case, we are just going to go ahead and obtain the exit code from that thread. And then we could do some checking on that. So we could say, do a little bit of checking for something like if the exit code is still active, then we can call terminate thread to try and force the termination of that. But chances are we're not actually going to need to do that. I've put this in here just as sort of a note. If we ever do want to handle that, that's the way we might want to handle it. But for now, I'm not actually going to do that. The only other thing that we're going to do is we are going to go ahead and close out that handle. And we'll go ahead and set the thread internal data to 0. We should probably also set the thread ID to 0, just to make sure. Okay, so that is destruction of a thread. And the next thing is going to be our detaching of a thread, which we've kind of already seen, so I'm actually just going to paste the whole thing here. And all this does is, again, we should probably also check thread for thread and thread internal data, meaning does it have a handle? If so, close the handle, which closes the handle itself, not the actual thread, effectively detaching it. And then we'll set the thread internal data to 0. Next, we have our cancel for our thread, and all this does is calls terminate thread if we have internal data. Again, we should probably check for the existence of thread and then thread internal data. We pass the handle to that thread, and then the exit code that we want here in this case is going to be 0. And then we go ahead and set the internal data to 0. Next, we have our check to see if the thread is active. And so in this case, we can say if the thread internal data exists, and again, we should check that the thread and the thread internal data both exist. We go ahead and get the exit code by calling wait for single object. And then from that, we get the exit code. So wait for single object, if we want to get the details on that, go ahead and pull that out. So this essentially waits until the specified object is in the signaled state or the timeout interval elapses. So in our case, we are not passing anything for the timeout, which in this case, right here, always returns immediately. So basically what this means is we do not want to actually block the main thread when we're checking for this. We basically want to say, okay, go ahead and get me the status, but do not actually block. And this will keep us from blocking on the main thread, okay? And we'll say basically if the exit code is wait timeout. In other words, the thread is currently executing, and this return timeout because we passed 0 here, meaning we don't want to wait. Then that means the thread is actually doing something, and we return true. If any of those conditions or false, then we return false, saying that the thread is not active. All right, next is just thread sleep. And again, this does the same thing as the Linux version of this. So this just calls platform sleep for the given milliseconds. This, again, should be called from the context of the thread that we want to use. We're just passing the thread here in case we want to extend this code later on for debugging purposes. But for right now, we're not actually using that. And then finally, we have our getThreadID, which calls getCurrentThreadID. Again, this would be something that's called from the context of the current thread. So you'd want to call this from the thread itself. It would say, what's the current thread ID? And we're go ahead and cast that to U64 and return it. And that is it for threads. That's all there is to it. The Windows version of this is actually, I find, a little bit cleaner than the pthread version of it, which is not something you'll hear me say often about Windows APIs, but this one actually happens to be pretty good in terms of the way that it works and the way that it's organized. Okay, so that is threads. Next comes our mutexes. So mutexes, thankfully, are not very complicated at all. So we only have just our 4 methods to implement there. So we have our kmutex create, which of course makes sure that we have an out pointer, right? And if we don't, we go ahead and fail on that. It also checks to see if we have. It also creates mutex. After that check, it says, okay, go ahead and set the internal data to create mutex. Create mutex is actually, there's the 2 versions of it, like so many other things in Windows. There's create mutex W, and then there's also a create mutex A if you are not using Unicode, but we are, so we're using create mutex. We just use this macro here to get the appropriate one. So if we go to that, that returns a handle. So it works very similar to creating a thread, and then all you really get back is a handle. The other thing that it does is it returns to us the name of a mutex, which is a little bit weird why it has a name as well as a handle. I'm not really sure why you would ever need a name, but it's there, I guess, if you want one. So in our case, we're actually not passing anything to any of these options. So we have attributes, which we don't need. We have initial owner, which we don't need. And we have name, which we don't need. So we're just passing 0 to all those things, and we're just using internal data, create mutex as it is, and setting it to internal data. Setting internal data to it. I apparently can't talk today. Anyway, next is we basically check to make sure that that internal data was set and that we did not get a null return from this for some reason. If we did, we go ahead and say, this is an error. We were unable to create a mutex, and we return false. Otherwise, we're going to go ahead and just return true. I did put a commented out ktrace in here in case we ever need to see mutexes being created and destroyed. We can see those in here as well. So with that, we've got creation there. Destruction is pretty straightforward as well. It's very similar to threads once again. So here we just check for mutex and mutex internal data. We close the handle if we have it. So the handle is internal data, if you recall correctly. Again, we have a commented out trace message here saying that we destroyed a mutex, and then we 0 out the internal data. The next is probably one of the more important functions, which is the kmutex lock. So once again, if we check for the existence of mutex and it's not there, we go ahead and call that a failure and return false. Next, we go ahead and call wait for single object. And this takes in the handle of the mutex. We have an infinite timeout for this. and we save that off in result. So when we call wait for single object, in this case, it goes ahead and attempts to get the mutex lock. So in this case, we actually want to switch on the result because there are a couple of potential outcomes for this. So the first thing that we can get is something called wait object 0, which basically tells us that the thread got ownership of the mutex. And in that case, that means our lock was successful and we can go ahead and return true. If we get wait abandoned, then that means that the thread got ownership of an abandoned mutex, which can mean that it was called from a thread that was maybe terminated or something like that. Or you're trying to call a mutex lock on a mutex that was created on a thread that was abandoned. Something along those lines. If we get that, that is considered a failure and we should return false. Otherwise, we are going to go ahead and assume a true result on that, because really this is the only thing that I'm aware of that we actually really want to catch in terms of debugging. So we should be pretty good to go on that. All right, so the last one is kmutex unlock. And again, this one's actually pretty simple, so I'm just going to paste the whole thing in here. We want to check for the existence of mutex and the internal data. So if we don't have one or the other of those, we return false. Otherwise, we call release mutex against the internal handle. And this basically just releases the handle and the internal mutex resource. Again, we have something here, trace that say mutex unlocked. And I don't actually think we had one for locked. So let's actually go ahead and put one in here right there. And we can also put one right here, just so that in either case, we know what we're dealing with. And here, let's go ahead and put mutex lock failed. And actually, let's uncomment this one and change it to AK error. So if we actually hit that error case, we'll go ahead and handle that. So the only other thing here is we need to check success. So result basically should return non-zero. If it returns a 0, that is a failure. And so we basically say the success of this is result not being equal to 0. And that is our mutex unlocking. So with that, let me just put in a note here and mutexes. So with that, let's go ahead and clean. Let's see. It says it could not find the file specified. Maybe that's because we haven't built it yet. Let's go ahead and build. Forgot how much longer this takes on Windows to build. Okay, so it looks like we have some unresolved external symbols. I wonder why this didn't get caught on Linux, but it did get caught here. So it's actually complaining that our camera system functions are unresolved external symbols. So I'm going to guess that that means we did not put KAPI in front of them. So camera system. Actually, is that camera system? Actually, it's both the camera system and the camera, I think. So camera system. So system initialized, that should not be exported, but yeah, none of these things are exported. That's why. So we need to export these. Okay, so camera system get default was one of those things, and then the camera itself, H file is probably going to be the same thing. So this is bleating about position, yaw, pitch, move forward, backward, all that. Yeah, this is the same thing. So we didn't export these guys either. So we'll go ahead and fill that out as well. Might as well fix that. I think we just need to export all of these, actually. So that is what I am going to do. All right. Because these are being called from the game outside the engine, these things have to be exported. So we have this decal spec DLL export that's required on Windows. So let's go ahead and build. See if I got them all. Looks like I did. Okay. And we're also going to go ahead and run our post-build task. Okay, and that ran successfully, so I think we are good to go there. So let's go ahead and close that out, and let's go ahead and run. And that opened up on my other monitor, so let me just give that a second and drag that down here. And it looks like we are good to go. So our window is showing up with the correct size and all that. Our various rendering modes look correct as well. We can swap our texture. That all still works. And yeah, I think we are in good shape. Let's go ahead and have a look here at our terminal just to see what our logs look like. So let's see. We have, let's see, should be in here somewhere. Before this, that's all renderer stuff. Still renderer stuff. Here we go. Okay. So here we go. So this is the same thing that we got on the Linux side, which is good. I don't know what that just tried to open, but okay. Let me just close that. All right. So we have 32 processor cores detected. We have 31 available threads. We have 31 reported. It will be capped at 15. So this is all appearing to work correctly, at least for right now. So obviously I will have to come back to Windows once we implement the job system and make sure that everything runs as expected, but we should be in pretty good shape for that for now. So that is going to do it for this video. I want to keep this one relatively short compared to some of the other ones. And the next video will be jumping back over into the Linux side, but that shouldn't really matter too much for you guys that are following along on Linux, because, or on Windows rather, because most of this stuff is pretty platform agnostic. There's just sometimes, you know, little bugs like this that sometimes I'll miss from the Linux perspective. So I'll try to hop over here a little bit more often just to make sure that things run as expected. But yep, that's going to do it for this one. So thank you guys so much for following along. I hope you guys are enjoying the series and learning. If you have any questions or comments, please leave them in the comments below. Hit the little like button there. It helps me out a lot. And if you haven't already, consider subscribing, because we're going to be taking this engine to some pretty awesome heights over time. And I really think you guys will enjoy some of the things that are coming forward. So anyways, thank you guys for watching. Have a good one. See ya.